Welcome to our fourth tutorial. In this tutorial, we're going to create a machine learning model to simulate a cart pole using reinforcement learning. The pole is attached by an unactuated joint to the cart. The cart is controlled by a linear actuator that can drive the cart left or right. The goal is to swing the pole up and balance it above the cart for as long as possible. You need to have the ProtoTwin Connect application installed for this tutorial. You can download the installer from our website. Start by downloading the CAD file for the cart pole at the top of the tutorial page. The first thing you need to do is import the GLTF file you've downloaded into our web application. We'll start off by adding behavior to the model like we did in our previous tutorials. First off, select the cart and add a physics component. You can leave all the properties to default here. Next, add a prismatic joint that will allow the cart to move along the x-axis. Now add the motor. The target velocity of this motor will be controlled via our Python script. Set the force limit to 100 newtons and the velocity, acceleration, and deceleration to 0. Remember to set the stall action to none as well. Now select the pole and add a physics component here too. Set the collider type to convex. Add a revolute joint and configure the axis and anchor points by selecting the features of the mesh where the pole is attached to the cart. Now we need to actually attach the pole to the cart, which you can do by setting the cart as the base for this joint. This joint is unactuated, but I'm going to add a motor, which will act as an encoder for reading the angle of the pole. Set the torque limit to 0 and all control properties to 0 too. Remember to set the stall action to none as well. Okay, and that's it for the model configuration. Last thing I'll do, which isn't strictly required, is change some of the graphics materials to make it more visually pleasing. Play the model to make sure the cart and pole are behaving correctly. Okay, reset now. Everything seems to be working okay. Now save the model and give it an appropriate name. The next thing we're going to do is go over the Python code for setting up our RL pipeline and model training with ProtoTwin Connect. You need to install a bunch of Python packages before we get started. The ProtoTwin package provides a client for starting and connecting to an instance of ProtoTwin Connect. Using this client, you can issue commands to load a model, step the simulation forwards in time, read signal values, and write signal values. The ProtoTwin Gymnasium package provides a base environment for Gymnasium for being used in RL workflows. The Stable Baselines package provides a reliable set of RL algorithm implementations in PyTorch. Signals represent I/O for components defined in ProtoTwin. Signals are either readable or writable. We can obtain these signal addresses from the ProtoTwin web application, which I'll show you how to do now. Select the cart and locate the ellipses to the right of the motor component. Click the I/O option under the dropdown. This will open up a model window that lists the I/O for the motor alongside the signal addresses. You can do the same thing to obtain the signal addresses for the pole. For the pole, we're interested in reading the angle and angular velocity, which have addresses 12 and 13 respectively. Next, we want to create a class for our cart pole environment by extending the vec-env-instance class. This is our base vectorized gymnasium environment for ProtoTwin Connect. Vectorized environments allow you to train an RL agent by stacking multiple environments into a single environment. This can help achieve quicker, more robust training and more exploration by allowing multiple instances of the same environment to run in parallel. We define some constants for the 10 millisecond time step and X threshold maximum cart distance of 0.65 meters. Next, we define a reward function that calculates the reward received by the agent at every time step. The goal of RL is simple: maximize the cumulative reward over the entire episode. In the RL literature, the reward is usually a function of the current observation and action. Our observation space is a four-dimensional vector that contains a measure of the cart's distance from the center, the pole's angular distance from the upright position, the cart's linear velocity, and the pole's angular velocity. The array stores the upper bound for each dimension. The lower bound is the negative upper bound. We use the gymnasium box space to define a Cartesian product of four closed intervals. For the first dimension, the interval is -1 to 1, and for the last dimension, the interval is -infinity to +infinity. Our action space is a one-dimensional vector that contains only the cart's target velocity. The interval is -1 to 1. Okay, back to our reward function. First, we define a reward term for how close the cart is to the center, remembering that 0 is at the center and plus or minus 1 is at the limits. We want to obtain maximum reward when the cart is close to the center of the track. We define another term for the pole angle to reward when the pole is balancing above the cart. We also define an energy or penalty term for the force applied to drive the cart. We call self.get to read the value of a signal from the ProtoTwin Connect client by passing the signal address. Finally, we calculate the reward as the weighted sum of three terms above. The constants we use here are hyperparameters, which you can tune or play around with. We return the reward multiplied by the time step to make it an appropriate value and clamp it above 0. The episode lasts for 10 seconds, so the theoretical maximum reward that can be obtained is 10. Next, we create a function that returns the observation at the current time step of the simulation. We read the current cart position, velocity, current pole angle, and angular velocity from the ProtoTwin Connect client. We then calculate the angular distance of the pole from the upright position. This mathematical expression outputs 0 when the pole angle is pi plus or minus 2 pi from the down position, i.e., at the upright position, and outputs plus or minus pi at the down position. I recommend you plot a graph of this function to understand how it works. We then return the observations. The first two values lie in the range -1 to 1 by dividing the cart position by x threshold and the pole angular distance by pi. The last two values are the cart velocity and pole angular velocity. The pole angular velocity we assume to be any real number lying in the interval negative to +infinity. The vector returned here corresponds to our observation space that I showed you a few minutes ago. Next, we override the reset function. This function gets called when an episode reaches a terminal state. We call the parent's reset function to reset the environment instance to the initial state. We call self.observations to return an observation of the initial state after the environment instance has been reset. We also override the apply function, which is responsible for applying the action in preparation for the next step of the simulation. We do this by calling self.set to write the current action value to the signal address for the target velocity of the cart's motor. Our action is a one-dimensional array, so we just need to access the first value of this array here. Finally, we override step, which steps the simulation environment forward in time by one time step. We first get the current observation, then calculate the reward by calling our reward function. We terminate the episode if the cart goes beyond the specified limits and truncate the episode after 10 seconds. We use truncated instead of done here, since our episode has a 10-second time limit, and we don't include the current simulation time as part of our observation space. We then return these values from our function. Okay, and that concludes the CartPole environment class. The final step involves creating an asynchronous main function that is responsible for setting up our training session. The first thing we do is call ProtoTwin.start to start an instance of the ProtoTwin Connect client, and we must await this function until the task is completed. The function returns an object for the created client, which is connected to the instance of ProtoTwin Connect. Next, we call client.load to load the ProtoTwin model we saved out earlier. Don't forget to await this function call as well. We pass the file path for the model. The name I gave when saving it out was CartPole.ptm. Now we can create our vectorized environment. First, we create some variables for the entity name called main. and the number of vectorized environment instances equal to 64. Now we can instantiate our vectorized environment, which we imported from the ProtoTwin Gymnasium Python package. We pass the CartPole environment class, the client object, the entity name, the number of environments, observation space, and action space. For the pattern and spacing, we just use the default values here, which will position our 64 CartPole instances into an 8x8 grid separated by 1 meter. There are other patterns available which you may want to use for other models you want to create. Next, we wrap this vectorized gym environment using the VecMonitor class that we imported from the Stable Baselines 3 package. This class is responsible for recording the episode reward, episode length, time, etc. We create a checkpoint callback function to regularly save the train model every 10,000 time steps per instance, so every 640,000 time steps in total. We also save the replay buffer checkpoints and the normalization statistics checkpoints. We save the models to the logs/checkpoints directory. Next, we define a learning rate schedule function that takes as input the remaining progress from 1 to 0 and computes the current learning rate using a quadratic decay with initial value 0.003. The basic idea here is that we want to take large gradient steps early on and much smaller steps later on for fine-tuning our trained model towards the end of the episode. Next, we define our machine learning model. For this tutorial, we use the proximal policy optimization algorithm. PPO is a policy gradient method for training our agent's policy network. This neural network is a multi-layer perceptron, which the agent uses to make decisions by mapping observations to actions. We also pass the monitored vectorized environment to the constructor. We use a mini batch size of 4096 and set the number of steps to 1000. This value represents the number of steps to run for each environment per policy update. A value of 1000 means we update our policy every 10 seconds. We also pass the learning rate schedule and the directory for logging the training progress to TensorBoard. Finally, we actually begin the training by calling model.learn with total number of time steps equal to 10 million and checkpoint callback for saving the model at regular intervals. Okay, and that's it. The last thing we do is we still need to call our main function using asyncio.run. All right, now's the time we can actually run our Python script. Go ahead and open a terminal and CD into your project directory. I'll just open the terminal in VS Code. Now run the command python main.py to execute our script. This will automatically open ProtoTwin Connect, load the model, create the CartPole environments, and start the training. I'll also open a new terminal to start TensorBoard so that we can see a graph of the episode reward. CD into the TensorBoard directory, then into PPO_1, and run the following command. You can now open TensorBoard on localhost port 6006. Okay, the training has finally begun. Initially, the agents are performing mostly random actions, but they quickly learn to spin the pole up. After that, they need to learn how to transition from spinning the pole up to balancing the pole upright, whilst minimizing the energy usage. Training this model usually takes about 1 to 2 minutes on my hardware, so I'll let it continue running. It runs faster than real-time too. Okay, they're all pretty much balancing now. Just one more thing I want to add. Keep in mind that the theoretical maximum mean cumulative reward that can be achieved is 10. But this is practically impossible, since this assumes that the poles are balancing upright from the beginning of the episode, without moving the cart at all, and without any exploration in the training process. And although the poles are balancing upright now, the carts are still shaking quite a lot. This is why we added the penalty term to our reward function. I'll let it run for a little bit longer so you can hopefully see the carts begin to shake less over time. Okay, and we're done. We've hit 10 million total time steps, so the Connect application should close now. The next thing we want to do is save the trained model so we don't lose it. Open your File Explorer. Go into the Logs directory, then the Checkpoints directory, and copy the last model checkpoint. Now go back into the root directory and paste the file here. And now rename the zipped file to model.zip. Okay, now we want to create a new Python script to export the trained PyTorch model to the ONNX file format. This will allow us to embed the trained agent into our ProtoTwin model for inferencing in the web application. And here's the export script, which you can find on the tutorial page of our website or on the ProtoTwin Gymnasium PyPy documentation. The first thing we do is import PyTorch, tuple, PPO, and base policy from stable baselines 3. Next, we create an export function and an un-nexable SB3 policy class, which extends torch.nn.module. This is PyTorch's base class for neural network modules. We call the superconstructor to initialize the internal module state and our agent's policy. We then override the forward method, which defines the forward pass for the neural network. This takes the current observation tensor and executes the policy network. We also set deterministic to true to ensure determinism across runs. We call ppo.load to load the saved model, and then create the ONNX policy object from the model we just loaded. After that, we call torch.onnx.export to export the ONNX policy, and call the exported file CartPole.onnx. And finally, we call the export function. Okay then, now we just need to execute the command python export.py to run this script. All good. You can see our ONNX file got saved out correctly. Now we are ready to do the inferencing. So go back into our web application again and open the ProtoTwin model. Open the script editor and create a new TypeScript file called cartpole.ts. And here's the script that does the inferencing. You can find this script on the tutorial page of our website. The first thing we do is import inference component, the base class responsible for handling the inferencing using ONNX Runtime Web, as well as the motor component and some other utility classes. Next, we export the class CartPole that extends the inference component base class. And then we create public handles for the motors of the cart and the pole and initialize these handles in the constructor. If you're unfamiliar with how handles work, please have a look over the scripting page on our documentation. We override the initialize async function, which gets called just before the simulation starts. We call the method this.loadModelFromFile, provided by the Inference component base class. This will load our ONNX file from the local file system. We also pass the dimensionality of our observation tensor and the lower and upper limits of our action space. But the ONNX file doesn't exist in the local file system yet. You can add it by dragging and dropping the file into the File Explorer to the left. Okay, now the script should know it exists. So we shall continue. The last function we override is the update async function, which gets called every time step. First, we access the value of the handles, i.e. the motor component of the cart and the pole, as well as the array of observations. Then we populate the observations array. We need to retrieve the current position of the cart, the current velocity of the cart, the signed angular distance of the pole from the upright position, and the current angular velocity of the pole. We then populate these values into our observations array, just like we did in our Python script for the CartPole vec-env class. And finally, we apply the actions. First, we call this .run to run our ONNX model, which performs the inference by executing the forward pass of our neural network, passing the observations array, and returning the actions. We must await this function as well since it is asynchronous. Then, we actually apply the action in the ProtoTwin model by setting the target velocity of the cart's motor. Okay, now we're ready to test it. Do you think it will actually work? Click on the main entity, then go ahead and add the CartPole script component we just created. Now configure the properties we defined for the cart's motor and pole's motor. And we're done. Now we're ready to actually run the simulation. Go into Navigate mode and click play when you're ready to go. And it works! And the cart appears to be not shaking at all. Perfect! Okay, this completes the end of the tutorial. You should now be able to create arbitrarily more complex models, such as a quadruped robot, or a bipedal robot, or a humanoid robot, or whatever else. Thanks for watching.